Yeah, that seems to work pretty well.
I can put food in a pot with a lid on, and then my cats can figure out how to open the lid.
Oh my god.
Yeah, they like vegetables. One of my cats really like vegetables. So it's really odd because this is like vegetable that is not even cooked. Okay, it's raw vegetable, just the green part, and then my cat go like that. The other one likes crunchy and salty food. So, tortilla chips, potato chips, The moment I open the bag, within 2 seconds, the fat cat would be next to me and go like, okay.
He's like, hey, you bring enough for the class?
Yep. Yep, those cats are funny.
Do your cats cry if you're like out of the room and they can't get to you?
Oh yeah.
Yeah.
Yep.
When we had cats when I was a kid, my dad had that treatment. He said like he couldn't take a shower if the cats weren't couldn't get into the bathroom and sit near the shower. They would just cry their eyes out.
Mine doesn't have tears. It's just
they would just be
just
like
making the
whining,
sound. Yeah, they can be very whiny.
Yeah.
The really interesting part is cats actually naturally do not meow. They don't make sounds like that. So if you observe feral cats, they only hiss at each other. That's the only sound they make. So they learn to meow and make those sounds to communicate with us.
Oh.
Yep.
That's cool.
So apparently we are the dumb ones. They have to learn, okay, let me speak your language. Meow, meow.
Well, they gotta accommodate us. Not.
Yep. Well, there are reasons why Egyptians worship cats, right?
Yeah.
When you have famines and rats, cats definitely are deities.
Oh, yeah.
There's no doubt about it. All right. So, I got it here. I thought I forgot again, but I did not. So this is freshly restapled this morning. I got it scanned last night and then restapled this morning. As it turns out, the stapler built into the copier at the division office, those staples are pretty hard to remove. So if you see, portions of the upper left corner torn off, it's not my temper. Okay, it's just because those staples are really, really hard to remove. They are meant to staple like 50 pages or more, and this is 2. So I don't even have the physical backing, to remove the staples, without hurting the paper. I can pass this back to you because there's no grade on it. For those of you who have taken my classes, you know that I grade only online. So I make a photocopy of everything. This way, it's much easier for me to grade online than to grade on paper. Because if I grade online, I don't have to carry this with me everywhere and worry about losing these. Okay, but once I scan it to Google Drive, it's on Google Drive, and it's up to the district and Google to back up everything. I mean, if Google Drive goes south, I'm pretty sure I'm not the only one who's going to suffer.
Way too much.
So, if there's no objection in the class, I'm just going to pass this in the class. Any objection? There's no grade on it, and you just look at yours and get yours.
So it's just
cool?
our copy to keep since you have a scan of it?
Yeah,
okay.
Absolutely. This is yours to keep. And if you know friends who might be taking this class next semester, you can share too. Absolutely. All right. So as you guys are busy doing this, I'm going to start up, propositional logic here. And yep, go ahead.
Just a heads up, Google Drive shutting down on December 11th.
On December 11th.
Yeah, and it will completely shut down in March next year.
And then what is going to replace Google Drive?
Something is coming up, yeah, but I'm not sure.
They just changed the name to Backup and Sync or something like that. So if
okay. So
that's what it was for mine because it was warning me about that.
Yeah, so I think it's probably just a rebrand, and because they're adding services to the whole thing. So I would imagine that they're gonna keep the content. It's just that they rename it. Yeah. I guess Google Drive is not a particularly attractive name. Only to people like us.
Because I was using the desktop app, where you can, where it has the folder on your desktop and everything, and it made me like uninstall it. Well, it was warning me like, hey, if you use it after this date, you will no longer have access to your Google Drive. So please download the download Google Drive is replaced with download backup and sync, and it's the exact same thing. They just changed the look of it a little.
I only use Google Drive using the web interface, so I don't think that's going to affect me too much.
No, it's only if you're a desktop user. I like it because I can just drop everything directly into the folder when I'm creating it on the desktop, but
gotcha.
I think I don't know if it's on Linux. I know it's on Windows and Mac.
Yep, go ahead. Sorry?
Mine wasn't in there.
Yours? Yeah, there are two piles, so it will cross at some point. Yep.
Mine wasn't in this section.
All right, so let's get back to propositional logic, and I hope you guys still remember some of that discussion. Okay, so let's zoom all the way out and talk about the rationale of propositional logic, why we want to study something like this, okay? Propositional logic is actually pretty, you probably get some exposure to this in philosophy classes, okay, because it is a really crucial part of logic, okay? But in computer science, it is particularly useful because of this particular topic here. It's automated theorem proving. I mean, there are many names for this kind of thing, but automated theorem proving is one of those. I don't know why they pop up this message because I made my donation already. It doesn't know because I didn't sign it. So ATP is automated theorem proving or automated deduction. It is the predecessor that leads to automated program verification, okay, which is a big deal. Because if you write a library, if you write some code, okay, to handle TCP/IP packet parsing, okay, how do you make sure that your code is 100% correct? Well, you can test it, right? But when people are testing it, especially in the good old days, they test it using the RFC. Okay, what is the full name of RFC? Okay, RFC, TCP. Okay, I cannot remember the abbreviation of RFC, but it's basically a published standard for something. Let me see if I can find the abbreviation. Okay, a request for comment. There we go. So an RFC is a request for comments, but a lot of times, the RFC also becomes the actual standard itself. So in this case, it basically specifies the entire TCP protocol. We're not going to talk about the TCP protocol. I'm just using it as an example. So as a protocol, if you scroll through any RFC, you will see a lot of this stuff like this, and then when you get to the functional specification, you get to stuff like this, okay? Which is okay. It's very tedious, but it's just technical stuff, okay? Which bit is responsible for what, and so on and so forth. Is that okay so far? So it is not very difficult. It's tedious, but it's not very difficult to write a program to recognize and be able to parse this correctly. It's not a big deal. The problem is, what if someone is maliciously, intentionally trying to give you a packet that is malformed, okay? That can be recognized as such, but if you're not careful, the window can be off, the pointer can be off, and so on and so forth. Is that okay? So writing a program, assuming the input is correct, and your job is only to parse it and to analyze it, is not a problem. Dealing with people who have malicious intent to break your program in any way possible, that is more difficult. Is that okay so far? Okay. So there are protocols and file formats, like the GIF format. Okay. So you can look up GIF, hack, and just kind of add to it. Okay. Let me see if I can remember the name of the Windows library that was causing this problem. Windows, I cannot remember, but I think the first few links will find it. It's Windows 98, and there was a problem with their graphics library. Automated Windows hack gives, no, that's not it. vulnerability. Okay. That is not what I want to know.
Maybe I'm thinking of something different. Wasn't that the Mac that it affected?
No, this was a long time ago. It was graphical files that was having the issue.
Security should be afraid. It's talking about the libjpeg exploit.
Mm-hmm.
Is that what you're looking for?
No, this one it predates that one, but it could be that one. Well, we can look at this one first. No, this is way too new. This is Windows 7. That one was a lot older. And I cannot remember the library that was causing the problem. So anyway, the exploit had to do with, inside the GIF file, you can actually, there's a field for comments. But there's a maximum length to it, like 254 characters or something like that. But it's supposed to be null terminated as well. So a lot of people, who are doing the parsing, assume the file was formatted correctly with 254 or less fewer characters. Okay, so what do they do to copy the comment to be displayed or copy it to somewhere else? String copy, right? strcpy string copy. So when you look up string copy, okay, you don't even have to go onto the internet. If you have any type of Linux installation or Unix installation, you can man strcpy, and it will tell you one thing. Right there, even within the man page, it says beware of buffer overrun, because it is only going to stop when it encounters a null character in the source string. If your destination only has 10 bytes, but your source has 16 bytes, guess what? It will copy the 10 bytes and then the 6 to overwrite whatever is after the destination, the end of the destination. Okay, so that's called buffer overrun. So as it turns out, the Windows library, processing GIF files, was using something equivalent to string copy to handle the comment field, and as a result, hackers were able to figure out what to overwrite and how to overwrite in order to gain access to the operating system through a GIF file. Okay, so we are talking about this kind of problem when we are talking about vulnerability and hacking and stuff like that. So how do you make sure that when you write your TCP, the protocol, parser, or when you have your parser to handle a GIF file, would not be susceptible to this kind of attack? That's the question. And how would automated theorem proving be useful in these cases? What do you think? Okay, how do you specify the correct outcome of a program? You can say whether it's, the file is recognized or not, okay? Or at least for a validation thing, you can say whether the file is validated or not. Is this a valid GIF file or it is not a valid GIF file? Does that make any sense? So if you look up the GIF RFC or the GIF standard, okay? And I don't know whether GIF has a RFC or not. Yep, it has its own specification, but it's not an RFC. But it looks really boring like the other one, okay? So you can use this documentation. Okay, let me see if I can find the right part here. Okay, so it has syntax, which is basically just describing which byte from what offset is responsible for what, okay? That's all it is. So if you read this documentation, it is not difficult to write a validating software to look at the file and say, is this a valid GIF file or not? So the outcome of your program is either yes, it is, or no, it is not. But you want to check to see if your program is only going to answer if and only if the file is actually valid. Okay? Is that making any sense or not? So your program, okay, let me see if I can. So you as a programmer is going to read through all of this documentation and say, okay, I need to make sure that the file follows all of these rules before I can declare this file is valid. Then we can do any further processing. But the validator itself may work, may not work, right? So how do you make sure that it is working? So the typical approach is you go onto the internet, right? You find yourself 20 gazillion GIF files, and then you feed all 20 gazillion GIF files through your program and see if it identifies all of these known to be good GIF files to be valid. That's great. But where do you find the invalid ones?
Same way.
Because that is the problem. Sorry?
It's that same way.
It's the same way?
The valid ones.
To find the
There might be some invalid ones there too.
But how do you find the invalid ones? Because anything that is published are most likely published or it is processed by the GIMP or some other image processing program that knows exactly what is the correct format. The incorrect ones are done intentionally by hackers. Okay, and there are many ways to make it invalid. Is that making any sense? So how do you check that your program can identify all the invalid GIF files? The valid ones are easy. Okay, you can find a whole lot of valid GIF files on the internet. The invalid ones are the problem. Okay, so automated theorem proving is basically saying, okay, we can prove that your algorithm is correct, step by step, so that by the time we get to the last line of the entire program, you have a proof to say that yes, this program is going to answer true if and only if the input GIF file is valid according to the standard on the projector right now. But it's a theorem proving kind of deal, which means you don't have to throw test cases at it. If it is proven right, then it is right for all cases. Is that okay? So for those of you who are interested, you can look into program verification and then look it up with the word security. Program verification technique for understanding security something. Security properties of software. We have formal verification, and inside here there's a discussion of security. There were some articles that I was able to find like within the last year or so. So this field is becoming alive again. It went zombie for many decades because in the past we did not have the processing power to actually do anything practical. Okay, the computers were not fast enough, so the best you can do is to verify a 20-line or 200-line program is correct. That's not really practical because real programs to parse any type of standard will be at least thousands of lines long. But now we have a lot more processing power, and as a result, we can now actually apply automated program verification to at least library modules that are crucial to the parsing of critical parts of, let's say, networking protocols or file formats and so on. So this field is now pretty active again. Okay, people are now utilizing automated theorem proving to help make sure that core parts of an operating system is in fact correct. We are not so concerned about the blue screen of death. That's not a major concern. Your computer just stops working. If your computer stops working, it's not leaking out data either. Okay, does that make sense? So what we are really looking out for are ways to get into the program, into a system, and then siphon information and data out of it. All right. So are we kind of having a big picture? Are we seeing a big picture of how this is applicable in computer science in general today, not 20 or 30 years ago? Okay. All right. So given that context, then what this is all about? Okay. Let me go back to what is propositional logic. This is alpha, which is defining the alphabet of the logic system. This is omega, it defines the operators. This is zeta, it is defining the transformations. And this is iota, which is defining the well-formed formulae that are known to be true to begin with. In other words, they are the seeds of all of the well-formed formulae. Is that okay so far? Okay, does it ring a bell? Because it has been like a week and a half before we touched on this topic. Sort of, okay. So the main idea is these two define what a well-formed formula should look like. Omega defines all the operators. It has subsets. Omega 1 will be all the operators that only take one single operand. Omega 2, will be all the operators that take two operands. Omega 3 for three operands, and so on. And then alpha is really just saying, okay, what are the symbols for constants? What are the symbols for variables? And what are the symbols for what we call schematas? Okay, I hope you guys still kind of vaguely remember all of these terms. Yep.
So this whole set right here, could it be considered like the C language is a set like this?
The C language is not a logic language, so I would not use C, but Boolean algebra can be expressed this way. So with Boolean algebra, alpha would consist of, if you like to spell out true, okay? I use 1 in this class. False is 0. You can use PQRST, lowercase, for the variables. Each variable is representing something that can either be true or false, okay? The schemata are the interesting ones. Schematas are only used in transformation rules. The transformation rules, each transformation rule is an element in Z, and the way it looks like is it has, okay, let me see if I can find the example here. So every element inside Z looks like this. On one side, we have a set of schematas, but in the specific form. On the right-hand side, you have, in this case, phi, which is representing, oh, this is a pattern that you can conclude with. Okay? This is called an inference. The symbol that looks like a T that is rotated counterclockwise 90 degrees, this one is called infer. So we are basically saying this particular pattern on this side, this set of patterns infers this particular pattern here. But the way it is really used, okay, is to say that if you can show that some WFFs of well-formed formulae to be true and they fit a particular pattern, and then you can apply this rule, then you can label another well-formed formula to also be true. So the idea is to spread that quote-unquote truthfulness of well-formed formulae until the theorem that you want to prove is labeled true again, labeled true. Is that okay? That's what we want to do. Do you guys still remember the analogy of using like red dots on a blue screen, sort of? Okay. So what we are trying to do is to spread the red dots until the theorem that you want to prove is also labeled red, because that means we're done proving it. Is that okay so far? Sort of? Okay. And yeah, go ahead.
What did you say about red dots?
Okay, so we can. So each red dot is representing something that is known to be true. Okay, so let me hook up this first. I'm looking at the time because I set up an alarm in my calendar to remind me to take roll. So I want to make sure that that mechanism is working. Okay. All right. So pens will work. Will work. All right. I only have one color today, so I'm gonna have to use circles.
You want to borrow a color pen? Or
No, I'm good. Thank you.
okay.
Okay. So that's. Okay. All right. All right, so I'll give you an example. So we'll say that alpha, this is really faint. Pretty sure I got a pen in here somewhere. Got a pretty good one. All right, so we'll just say that alpha equals to a set that has 0, 1, P, Q, R, S, T, and then we just have a whole bunch of size, fives, row, and so on. Okay, is that okay? So I'm just defining a set of alphabets. It's almost the same thing as alphabet in any language. Okay, any alphabet-based language, we're just defining the basic blocks of things. Omega in this case, okay, if you're dealing with normal Boolean algebra, then you have negation, which is actually in omega 1, but omega is the superset of all of the unions of the omega 1, omega 2, and so on. You have conjunction, you got disjunction, you got implication, and we'll just say that that's all that we want to deal with. Okay. So with these two, we can now state what a well-formed formula should look like. Okay, a well-formed formula is just picking something from here. Anything from alpha is automatically a well-formed formula using the most general sense of propositional logic. But if you use the correct number of parameters in an operator, then any well-formed formula. Okay, so in this case, if you have a well-formed formula, you have another well-formed formula, and then you say the conjunction, that whole thing is a well-formed formula as well. So the definition of what a well-formed formula is recursive. Is that okay? So this allows you to make really, really complex well-formed formulae. Because the moment you combine two well-formed formulae using an operator, that whole thing, assuming it is the right number of parameters, that entire thing becomes a well-formed formula. Yep.
So as long as you use the right number of operators on that.
Oh yeah,
then
absolutely.
it's a well-formed formula.
You may have something that doesn't make any sense. Okay, you can end up, in this case, I can end up with P is a well-formed formula, P and P is a well-formed formula, P and P and P and P is well-formed. And then if you take this entire thing and itself, it is well-formed again, and so on. So it can generate an infinite number of well-formed formulae and many of those may be totally meaningless. Okay, they're duplicates of each other and so on. But that's only when we use semantics, when we associate meanings to it. This system has no understanding of semantics or meanings. It only understands syntax. Is this that? That's all it understands. It doesn't understand, implication means that when the first one is true, the second one has to be true. Nope, doesn't understand it at all. Implication is nothing more than a symbol. Is that okay? All right, yep.
What makes it not a well-formed formula?
Something like this. Okay, we have a P not Q. That would not be well-formed. Or you have a conjunction with all by itself, that is not well-formed.
Why not? Why is that not well-formed?
Which one?
Either of those.
It's not well-formed because it is not well-formed by the definition. When you use an operator, you have to supply the correct number of parameters. And each parameter has to be a well-formed formula.
But you just use an operator and parameters with P and P.
This is P and this is not Q.
I know, but the other one that you said was correct.
This one, by itself. Conjunction by itself is not a well-formed formula. These are. Everything on this side, they are well-formed. This is not well-formed. If you say P and, that is not well-formed. When you say or Q by itself, it is not well-formed. Yep.
So what if you did P or not Q? That's a well-formed formula?
Okay, not Q itself is well-formed.
Yeah.
P is well-formed. So when you have two well-formed formulae, and then you combine those using an operator that needs two operators, operands, then it becomes well-formed again.
So the meaning of the operator changes.
Ooh, that's a good reminder. It's intentional. I chose something that is not particularly disruptive.
Go for that.
There you go. Okay, so are we okay so far with this?
So if the operator is like, okay, because you said the operator can be a one-element operator or a two-element
Right, because negation is the only one that is one element, and then we have all of the other ones are two. But this is only this is because of the way we define Boolean algebra in a normal sense.
So as long as it matches the number of elements that the operator is supposed to have, then
Yep.
it's working.
Yep. Yeah, go ahead.
So if the operator requires more, two operands, then it has to have two if it's a well-formed formula.
Okay, if an operator needs two operands,
like
needs
conjunction
two,
or dissection.
with a conjunction, you need to give it two well-formed formulae, and then when you make a composite out of the two sub-well-formed formulae and the operator itself, that whole thing becomes its own well-formed formula.
Oh, okay.
Is that okay? All right, cool. All right. So are we okay so far with, we can, just using a very small, set of alphabet and a very small set of operators, you can generate a huge infinite space of well-formed formulae. Yep.
So the definition of a well-formed formula is however many, the number of operators matches the number of operands within the formula.
Correct. Yep. Because the other way to look at AND, because the confusion comes from the fact that we use infix notation. Okay. So because of the way we use infix notation, like we say P and Q. Okay. So by the time you write P and Q, it has to be syntactically correct, or it has to be a well-formed formula. But in general, when you're talking about operators, it really should be written like this: and then PQ. Okay, just like the way you define functions or use functions in C and C++. You state what you're going to do, and then you say, okay, what do I need to do it with? So in this sense, okay, then AND with just one single operand would not be right, because it is expecting two. Okay, with negation, it should only be expecting one. When you give it three, this will not be valid. So this is not good. This is not good. This is okay. Yep.
If one of the operands we use isn't an alpha, is it automatically not well-formed?
No. The operand only has to be a well-formed formula. So it doesn't have to be in alpha. Okay. In other words, if you nest things like this, that would still be okay. Let's see. I'm just trying to. Nope, one more operand. There we go. So this would still be okay.
What I meant is like y isn't an alpha. If we did not y, what would we be able to say about that?
If a symbol is not in alpha, you cannot use it in a well-formed formula. Yep. So that is correct as well. Yep.
The last one, you need. Never mind.
Okay. I like those questions. So are we okay so far with well-formed formulae? Yep.
Just in that last part, I'm a little confused on why that works.
Okay, so let's work on this from the inside out. Is this well-formed? Seems well-formed to me. Is this well-formed? It's an OR, it has two operands, it's good, right? So this by itself is a well-formed formula. This is a well-formed formula as well. So can I use these two to make conjunction? Okay, so this conjunction by itself is well-formed. Can I use the conjunction as the operand of negation, which only expects one thing? Okay, so there you go. So when you look at this, you can also look at it as a syntactical tree, which means you have a negation on the outside, and then you have a conjunction here. The conjunction needs two things. The first thing is an OR, and then the OR is using just P and Q. On the other side, it has a negation, and what it is negating is R. So you can also look at it as a syntax tree, so to speak. Is that okay? In other words, if you're looking at a well-formed formula as a tree, it's basically saying a well-formed formula is only well-formed when each subtree from the top level perspective is well-formed, and you have the right number of subtrees for the top level operator. That's a recursive definition of how you can use this. Is that okay? Just different ways of looking at things. And I'm not even going to bother to look into Polish notation, reverse Polish notation. RPN? Oh, RPN is great. Okay, since I said that, I have to get into it now, right? So next time, when I say I'm not even going to bother, that means I'm going to talk about it next. Okay, so one reason why people do not like, well, there are two reasons, but there are two reasons why the prefix notation, which is what this one is not really particularly friendly. One, to people, it has a lot of parentheses, so you need to match parentheses a lot. And from the machine's perspective, it is not easy to parse because you need to have a stack to keep track of, okay, how many levels of parentheses have I opened, and this is closing which parentheses, and so on. So, and so that's why we have RPN, or reverse Polish notation. Reverse Polish notation for this one is going to look like this. It's going to be P, Q, or R naught, and then we have AND, and then we have negation. Okay, so the way RPN, or reverse Polish notation, works is when you have values or variables, it's just pushing it on the stack. When you have an operator, it pops the right number of things from the stack, and then it pushes the result of the operation back on the stack. So you're pushing P, you're pushing Q, you pop those two, you perform the OR, and then the result of the OR is pushed back onto the stack. Okay, we're not doing anything with that yet. We push R on the stack, we pop the R from the stack, we perform the negation, we push the negation of R back on the stack. So now we have two things on the stack, right? The first one, or the deeper one, is the disjunction. The second one, or the top one, is the negation. Then we perform a conjunction using those two things, pop those two from the stack, perform a conjunction, push the result of the conjunction back on the stack, so we have one item on the stack again. Then we pop that, we perform the negation, and then we push the negation back on the stack. In other words, this infix notation, this prefix notation has the same can be represented using this postfix notation. And look, no parentheses, no commas. Yep.
So you're evaluating it and then pushing?
Sorry?
So you're evaluating each one and then pushing it?
Right.
Okay.
So every time you encounter an operator, like the disjunction, or the negation, or the conjunction, you are popping the right number of things from the stack, perform the operation, and then you push the result of the operation back on the stack. Yep. Do you guys like RPN? Yes? Okay. To a machine, it is very friendly because the parser to deal with RPN is like this long. Because it's already sequenced correctly. And that's why older HP calculators can only use RPN because they did not have the processing power or the memory to deal with parentheses. Okay, you guys look at me and go like, what? HP made calculators? What are you talking about?
I know that.
If you have parents or uncles who were engineers in the anywhere from the 70s all the way up to the 90s, and ask them about scientific calculators from HP, they will tell you everything that you need to know about those calculators. They were expensive, but very cool. All right, so are we good so far with what is a well-formed formula? Okay, it is the idea that counts. Okay, whether you use the infix notation in the previous slide, the prefix notation, or the postfix notation, it really doesn't matter. They express the same thing. Are we good so far? Are we also convinced that the space of all the well-formed formulae is infinitely large? Okay, it should be pretty clear that we can just make senseless well-formed formulae just by using those few operators. Is that okay? All right, so now imagine that you have this space here. I know it's infinitely large, but I'm going to use this square or rectangle to represent the space of all the well-formed formulae. for a particular calculus, a propositional calculus system. So some of these, okay, are labeled. So some of these are labeled. I'm going to use a circle around the dot to say that they're labeled. Okay, so some of these are labeled initially, and others are not labeled initially. They're all over the place like that. Okay, are we doing okay so far?
Labeled how?
Well, that's the next thing. So all of these ones that are labeled, they are elements of I, or iota. So the set iota consists of all the well-formed formulae that are known to be true, given to be true. Don't ask me why these are true. They are just true to begin with. Yep.
So everything in A, in alpha is in I.
No, that's not what I said. Everything in A and everything in omega spans this entire space, the rectangle itself. But when you look at which ones of those should be labeled, is the I, the set of I, which is finite, tells you what is true to begin with. Yep.
So I is defined by whoever is using the system, sort of like.
Yeah. Whenever you want the system to model, I and zeta, together defines the mechanics of the system. So in the physics engine, for instance, I'll get back to you. So in the physics engine, I would be the constants like gravitational pull, all the physical, natural, constants. Those things will be in I, because they are known to be true or known to be that value to begin with.
For that specific system.
For that particular system that you're emulating, correct? Yep. Go ahead.
So when you said like PQ and R naught and all that stuff, would that be an element of I?
Can be, doesn't have to be. So your I would consist of the constants, or one constant has to be true, right? So 1 is in iota, but 0 is not. The negation of 0 is. Okay, so when you look at what is in I typically has 1, which is true. Not false is also known to be true by definition, right? It has 1 and 1. These are all in the notes, okay, so I'm not going to repeat too much from the notes itself. So you have a whole bunch of stuff that is known to be true, but then again, you also have some specific ones, like P implies Q. For whatever reason, I tell you P implies Q is true as a well-formed formula. Don't ask me why. It's just known to be true. Okay? If tax is a boring professor, then at least half the class is going to fall asleep in his class. That is known to be true. Throw it into the iota. Is that okay? So the iota starts with all of these things, which are represented by dots in the well-formed formula space that are circled to begin with. Is that okay? So now we have one particular dot here. Okay, I shouldn't circle it. Square. There we go. So the square one is your theorem, something that you want to prove. You're basically asking, given everything that we know to be true to begin with, can we show that that square thing is also true? That's the objective of proving. Is that okay? So in this case, the square thing may be representing people who have a class, right after tax class. They always feel that in the second class, they always feel refreshed because they slept in tax class to begin with. Okay? But do we have enough, mechanical? Do we have enough mechanics to make it happen? That becomes the question. Okay? The transformation rules basically are pattern matching kind of things. So they say, oh, if I see something of this pattern and I see something of that pattern, then something else has to be true too. So every time you apply a transformation rule, you're basically combining a few things. Okay, you're combining this or this and into one thing. And you look at this and go, oh, because these two are known to be true, you know what? That dot is known to be true too. But this has to do with a transformation. This is an inference using that symbol. Yep.
Would De Morgan's law be considered a transformation rule?
Say that one more time.
Would De Morgan's law be considered a transformation rule?
the Morgan's law should be represented as a transformation rule. Yes. But remember, we are not dealing with actual logic here.
That's only
We are only doing syntactic manipulation. Yep. Is that okay? So the same thing can be done. Let's say this one by itself infers this dot here, and then this dot infers this one, or these two combined infers this one, and then this one infers this one. I'm just using this as an example like that. Okay, so eventually if you can use all of these things, you keep spreading the circle. If you can eventually label the square one also using a circle because of transformation rules, then you have just proven that the square one is in fact a theorem, because it is the result of, or the consequence of iota, the elements of iota. Is that okay so far? Okay. But you can probably see that this is not going to be easy. It's not going to be easy because we got transformation rules that can go in the wrong direction forever. So here's I think I might have an example here. Nope, I do not. But I have some examples like this one. This is a transformation rule. So this transformation rule is basically saying, okay, getting back to the picture. Okay, let me explain what this means first. So what this means is I can use an empty set, which means I don't need to know any well-formed formula that is actually true, but I can infer that give me any well-formed formula or the negation of itself. I can label that one. I can circle that one. Is that okay? So in our picture, what does it look like? So let's say this dot here is, when I spell it out, it is some variable p or not p, okay? That's what that dot is representing. Does it fit this general description? Remember, the Greek letters, they are placeholders. They're basically wild cards. In this case, psi is really just saying, I can be any well-formed formula. And then the other side, which is not psi, the second side is referring to the first side. Okay, it's basically saying, if I have some kind of well-formed formula, a or, and then the negation of that well-formed formula, this entire thing, the disjunction itself, is known to be true. Is that okay? In other words, this is a transformation rule. It specifies the pattern. This is the actual well-formed formula that you can label in the space. But I can make that label without even using anything from iota, because that's what the rule is specifying. The rule is basically specifying and say, okay, let's go through every single dot in this entire space. Okay? And then for each dot, okay, for each well-formed formula, we'll see whether it fits that transformation rule or not. If it fits, we circle it. And you can probably imagine that there's an infinite number of things that we can circle here. Is it going to help with proving your theorem? Maybe not. So that is the problem of propositional logic, is you have no idea when it is going to conclude. Now, if the theorem that you want to prove turns out to be false, it is not actually a theorem, when do you say, okay, we're giving up, this is not a theorem? Remember, this space is infinitely large. Okay? Just because you have not found, you have not labeled it yet, doesn't mean it won't be labeled in the future. So how much time are you going to give the algorithm before you make a conclusion and go like, I guess it's not a theorem? Yep.
You have to somehow prove the contradiction.
That's where we're going. Yep. So that's a very good idea. So that's exactly where we are going. But that's the limitation. Okay. This is the limitation. Propositional logic was invented long before computer science. It was invented by, not invented, but it was talked about by philosophers, who basically want to kind of talk about the meaning behind something versus the syntactic manipulation of symbols to represent the same thing. But in computer science, we are much more pragmatic. Okay, we want to be able to conclude whether a theorem is true or not within a known amount of time, one way or another. In other words, if the theorem is not true, we want to make that conclusion and say this theorem is not true within a reasonable and predictable amount of time. If the theorem is in fact true, we also want to be able to prove it is true within a reasonable and predictable amount of time. Is that making any sense? Is that okay? All right. So getting back to the notes here, we are done with a whole lot of discussion like this. We'll get back to completeness and soundness later because I want to kind of follow this thread and move on to resolution. Because resolution is a mechanism, is one of the key pieces of a mechanism to make sure that we have a system where you can express any Boolean expression that you need to. That's one criteria. The second one is the algorithm will terminate within a reasonable amount of time. It is predictable how much time at the most it can take. And three, it will make a conclusion either way. If your theorem turns out to be true, it will tell you it is true. If your theorem is not true, it will tell you it's not true, instead of spending an infinity amount of time trying to search for the right answer. Is that okay so far? So think of it this way. I'm telling you that there might be a needle in a haystack. Okay? So you're trying to find a needle in a haystack. But the problem is the haystack is infinitely large with the original propositional logic system. So you have an infinitely large haystack, and I'm saying that there might be a needle in it. Go find it. Isn't that going to be a problem?
Like asking to find the function for all primes. It's out there. You'll find it. Just keep working on it.
Yep. So that's the problem. So even though I give you the tools, like a limited range metal detector and stuff like that, you have the necessary tool to go from one part of the haystack to another part of the haystack and so on. But you can never really finish unless you actually confirm and say, okay, this is the needle, I found it. Okay. But if you walk in the wrong direction, you will just keep searching. Or if the needle is not in the haystack to begin with, you will just keep searching. That's not what we want to do. We want some mechanism where we will say the haystack is only so large. Okay? It's not infinitely large, it can only be so large. Okay? This is it. Okay? And you can just systematically go through the haystack and go like, okay, it's not here, it's not here, it's not here, it's not here. And after a certain amount of time, you can make a conclusion. There's no needle in this haystack. You lie. Okay, that's what we want. And resolution is the way to do it. So the way resolution works is, this is a proof by itself, okay? So what we want to do is to find out why this makes sense, okay? Because this implication will turn into an inference, okay? But before we turn it into inference, we have to make sure that this works logically. So what I want to claim is to say logically, this is not inference, this is not propositional logic, this is actual Boolean algebra. So what I want to claim in Boolean algebra is you can tell me phi or psi, the whole thing, and not psi or rho, the whole thing. That implies phi or rho. Okay? In other words, all that we are doing is to merge this expression with this expression, but quote unquote, the psi and not psi cancels out. Okay? But why does it work? Okay? Yep.
Because it can be true or false. Either way it will be true.
Well, that's not exactly how I proved it. So the way I proved it is actually step by step using Boolean algebra. So I'll go through this quickly. So this is the original one. And the first thing I'm going to do is to get rid of this implication. A implies B is not A or B. Okay, that's how we get rid of the implication. So that's why I'm negating this entire side and then do an OR with the second side. So that's why you see this negation. This entire thing is the left-hand side of the implication, and this part is the right-hand side of the implication. Is that okay? Yep, go ahead.
Did you already go through that in class, how that works? Like you proved that you can turn implication into the other thing?
Yep. It is also by definition too. So implication A implies B is by definition not A or B, but you can also prove it using a truth table. Okay?
Which we're not going to do, right? Use truth tables?
Huh?
Which we're not going to do, use truth tables?
Truth table will be the easiest, but the definition, but it all boils down to the actual definition of implication, which is, false implies false is true, false implies true is true, true implies false is the only time it is false, and then true implies true is also true. That is the actual definition of implication as a logical operator. Is that okay? All right. So how did we go from the first row to the second row? What just happened here? There are two things that happened. Sorry?
Oh, I answered your question.
Okay, good. Okay, so two things happened. The first one is I applied De Morgan's law with this negation of an end, and then with this part it is just associative, property of disjunction. So I just took out the parentheses because we have an or on the outside already, so the parentheses were not necessary. This part here is De Morgan's law. The negation of a conjunction turns into the negation of each individual component, but the operator goes from conjunction to disjunction. That's De Morgan's law. How did we go from the second row to the third row? We applied De Morgan's law again, right? So we applied De Morgan's law with this expression, so it turns into this one. We applied De Morgan's law to this expression, and it turns into this one. Is that okay? How did we go from this row to the next one? This from here to here. I used some really kind of awkward thing, didn't I? So instead of just saying phi and row, I use phi and true, and instead of saying row, I say row and true. But does that really change the meaning? Anything and true is that original anything. In other words, true is the identity with respect to conjunction, just like 1 is the identity of multiplication. Is that okay? But in normal algebra, you would normally you normally don't do something like this, right? You introduce something that doesn't seem to be useful. And then from here to here, it looks even more senseless, because I turn that true into psi or not psi. Is that okay? Do we know that psi or not psi is always true regardless of what psi is? Yep. Okay, so it doesn't seem to make any sense from the perspective of why are we making things more complicated? I thought we were trying to simplify things. But at the same time, it is not wrong either. Logically, it makes sense. Is that okay? Intuitively, it's like, okay, I think we're heading in the wrong direction. Okay? So what about going from here to here? Which rule of Boolean algebra do you think I just used? You have something like this in normal arithmetic algebra as well. It's distribution. Okay, it's just distribution. So I'm distributing the disjunction over the conjunction. Same thing over here. Okay, so once we get there, I rearranged things a little bit so that see how we have this term here, and see how we have, where is it? This term over here. So I use factoring this time. In other words, I say that, hey, they're both doing conjunction with not psi. Why don't we just combine both of those, with and not psi together, and then we just have a disjunction to deal with the not phi on this side and the phi on this side. So this is just the factoring, the result of factoring between this expression and this expression. This one is the result of applying factoring, but using this term and this term, the last term here. Okay, and these two were just kind of leftovers. We'll just let them stay around for a little bit. No big deal. So when you look at this term, what does it look like? Yep, we have a conjunction here.
So it doesn't matter.
Yep. So we have a disjunction of phi and phi not phi. So that turns into a 1. And then same thing applies here. Rho not rho with a disjunction turns into a 1. So we end up with just that and that in the disjunction. But wait, that by itself is true. True or whatever is always true. So that's why we have one single conclusion of just true. Okay, what does that mean? Okay, what does it mean? It means that this expression is always true. And I mean, so how is that going to be helpful? How this expression is always true. So is rho or not rho. That's always true. Okay. How is this any better than that? Well, it's better than that because it's an implication. So when an implication is always true, you can use it as a rule now. It is a valid rule to use because the rule itself is always true. Is that okay so far? Sort of? Maybe? Okay. So what this means is whenever you see something like this, you can always make a conclusion like that. Hey, if this makes sense in a logic sense, how about we code it into a transformation rule? Is that okay? So when we code it into a transformation rule, it's just this. In other words, in a set, I'm looking for something that looks like this. Now, given I found something that looks like this, then I need to find something else that looks like this. In other words, the psi has to be common between these two. If the first expression has a disjunction with psi, I need the second expression to have a component of not psi. Is that okay? The rho can have nothing, absolutely nothing to do with the phi. That's okay, not a problem. But I do need this one piece that connects the two. If I can find a well-formed formula that is known to be true that looks like this, I can find another well-formed formula that looks like this that is also true, then I can label this well-formed formula and say that, hey, you know what, you are true too. But this is all syntactic, okay? I'm just doing pattern matching here. But we're still doing okay so far with resolution. So as it turns out, in a system using resolution to prove something, this is pretty much the only transformation rule that is really important. The other ones are just exchanging the order, associative and also commutative. Those are pretty easy to understand, but this is the real one that is kind of tricky. Okay. So what we ended up doing is to modify our propositional logic system so that in omega 1 we only have negation. That's the only thing we are allowed to do with only one operand. No change from before. But what is interesting is omega 2 is also a singleton set, which means it has a single element of OR. What about AND? We don't need that. What about implication? Don't need that. We just need negation in omega 1 and disjunction in omega 2. That's all we need, which is really, really cool. But then we also have to define what a well-formed formula is slightly differently. So what this is saying is if you find for all elements in A, in alpha, that element E is automatically a well-formed formula, but I'm using WFF1 to qualify. In other words, it's not the overall well-formed formula, it is a sub-well-formed formula. Is that okay? For any element E in alpha, the negation of that is also a well-formed formula, but it's only a sub-well-formed formula. In other words, it is not an overall well-formed formula that I want it to live in the space itself, but it is just a component of a well-formed formula. So WFF1 is only saying that you can use it as a component of a well-formed formula, but by itself it is not yet a well-formed formula. Is that okay? Questions? Yep.
What's the difference between the one with the E and the not E?
E is just a symbol from alpha, and not E is the negation of that thing from alpha.
So if it's not from alpha, then it's different.
No, that's not what it says. It says if 0 is from alpha, then not 0 is a well-formed formula. It's a component. If P is from alpha, then not P is a component of a well-formed formula. Is that okay or not? By the time we get here, by the time we get to the part that is highlighted, E is already known to be an element of alpha.
I thought of being an element of alpha was already meaning that you were well formed.
Not in this, we're modifying the system. So in the new system, this is modified.
Okay.
So the way we qualify an expression to be well-formed is now different.
All right.
Yep.
So in the new form, is it possible to have elements in alpha that are not well formed?
Say that one more time.
In this new way of defining the system,
Right.
is it possible to have something in alpha that is not well formed?
In fact, everything in alpha by itself is not well-formed entirely, because okay. So let's read the third one. So the third one says, for all I from 1 to n, if all the phi i's are components, valid components of a well-formed formula, then the disjunction of all of those terms is now well-formed. Okay, examples. Okay. So let's say we keep alpha defined exactly the same way as before. Okay. So we're only changing the other parts. P is not well-formed anymore. Yep.
Are you basically just saying that a formula without an operator isn't well formed?
No, not quite. Not quite. Okay, so let's just say that is a WFF1. So we'll look at the ones that are true. Okay, that's true, right? Because P is from alpha. Is a WFF1. That's true too, because 1 is also from alpha. Is that okay? Is a WFF P or Q is false. This is not true. This is true and this is true. Is that okay? Because this is an expression. It's not something from alpha itself.
It has to be an element.
It has to be an element from alpha. Okay? Is a WFF1, sorry, I'm missing a 1 on all of these. That one is true too. So WFF1 is only saying that it can be a component in a WFF, but by itself, it is not. Is that okay? More or less? Okay. What about P or Q? Would that be a well-formed formula? P is a WFF1, Q is a WFF1, and according to this rule, it says as long as each component of a disjunction, as long as each one is a WFF1, then the disjunction of all of those is a well-formed formula. So according to that, P or Q is well-formed. P or 1 is well-formed. 1 or 0 is well-formed. P or not Q is well-formed, because not Q is a WFF1 because it's the negation of a thing from alpha. Yep.
What is the difference between the above P or Q and below
P or Q. Okay. So it's the same. P or Q is the same, but P or Q is not a WFF1. It is a WFF, but it's not a WFF1. Yep.
So the bottom P or Q is part of I?
You mean here?
Yeah, no. Like that P or Q together is a part of I.
You mean here?
No, the bottom.
The bottom. You mean here?
Yeah, the first one you were pointing to the left. Yeah, that one.
Okay.
Is that part
No,
of
no, I'm not saying, this has nothing to do with who's in iota. This has to do with what is that entire space of well-formed formula. What does each element look like in the space of well-formed formulae? Is that okay? Yep.
So WFF1 is a new qualification for.
Is a new qualification invented only to deal with resolution.
Okay.
Yep.
So we wouldn't use it for the earlier.
It wouldn't. You would not use it in the general propositional logic, but it is necessary to use. It's necessary to use it as a notation to define what a WFF should look like when we have to utilize resolution.
Is there also a WFF2 or anything like that?
No, just WFF1 and WFF. Yep. So P or true or not Q, that's well formed too. Okay. So are we doing okay so far with what is well formed? Okay. Not P or Q and then the whole thing or R is not well formed. Why is it not well formed? Because when you use a disjunction, each side has to be a WFF1. This is not a WFF1. Well, it's not a WFF1 because this entire thing is not an element in alpha. Is that okay? Okay, so there's a quicker way to say that. The quicker way to say that is in order for something to be a WFF, it has to be a disjunction of, okay, each thing, in each component in this disjunction can only be something from alpha or the negation of something from alpha. That's what I'm trying to express. Are we still doing okay so far with this? Sort of? Yep.
Could you convert that into something that's well formed? Could you convert that into something that's well
Yes.
formed?
Okay, so here's the thing. So the thing is, on one side we have the conventional Boolean expression space. Boolean expression space, which allows you to say, P implies Q, the whole thing, or R and not S. Something like that, okay? It has things that you normally use in Boolean algebra, normal expressions. In the other space, which we will call C and F, or conjunctive normal form, okay? We have all of these WFFs that can only be disjunctions of variables and constants, okay? So now you can only have P or Q, Q or 1, P or Q or R, P or not Q, and so on. Yep.
I thought it was called DNF, disjunctive normal form.
This is actually conjunctive because the conjunction is implicit. Yep.
Is not Q is an element?
Not Q is fine. Not Q by itself is technically not well formed, but not Q or 0 is. So not Q or 0 can be here. It depends on how you define the big V notation, but you can always attach not or false to anything to make it a well-formed formula.
Does not Q have to exist in alpha?
Q has to exist in alpha, and
not
0 has to exist in alpha in order for not Q or 0 to be true, to be well-formed.
Do you need Q and not Q?
Q and not Q. What about Q? Are you talking about Q conjunction not Q?
No, like in the set of alpha.
Alpha only has Q.
Okay.
Negation is from omega.
But yet we can't use the negation on the other one.
You cannot use a negation on an operator. You can only use a negation on something from alpha. So you can say negation of a constant, you can say negation of a variable. Yep.
So I'm trying to understand what redefining what a well-formed formula is, what that would do for us.
Okay, so that's a very good question. Okay, so before we go there, we have to answer this really big question. Are these two spaces equivalent? If I say this is true in this space, can I label the right ones on this side to express the same thing. If you give me any, so the conjunctive normal form is basically taking these things and make a conjunction out of them. So when we go back to the notes, there's an example. Let me show you the example. I think that will really help to illustrate what we are talking about. This looks like a pretty normal Boolean expression. It has implication, negation, conjunction, and parentheses to indicate nesting and stuff like that. Is that okay? So this is the conjunctive normal form. Okay, forget about the derivation for now because I just want to kind of skip to the point here. So this is conjunctive normal form. When you look at the conjunctive normal form, it is one huge conjunction, but each component, what does it look like? It's a WFF. This is a WFF. This is a WFF. Is that okay? Then where is that conjunction going inside this space? Okay, so if I switch back to this picture here, when you look at this C and F space, where's the conjunction? The conjunction is implicit. Everything that you circle, everything that you label, they are all inside one big conjunction. So that's why it is called C and F, even though each thing that in this space doesn't have a conjunction. That's only because everything that you label, all the things that you circle, implicitly they are all inside a huge conjunction. And that's why it's called a conjunctive normal form. Is that okay? We still have 2.5 minutes to go. I'm going to use those. Okay, so when you use resolution, okay, I'm skipping proof by contradiction. We'll get back to it on next Monday because it is important to go through with that. But it is also important to go through resolution, which basically is here. Okay, so forget about this part. If I give you a conjunctive normal form that looks like this, oh, by the way, this P is not supposed to be here. The P is supposed to be P or 0. The Q is supposed to be Q or 0. So just kind of look at those as something with an or 0, because or 0 or false doesn't do a single thing. False is the identity with respect to disjunction. So the idea of how did I generate this not Q here? Is resolution. The resolution is identifying this expression containing a not P. Is identifying this expression of having P. So the P and the not P cancel out. So I end up with not Q with an or 0 that is implicit here. And that's why I can make a conclusion of not Q. That's one step of resolution. Then I take this not Q, and then I look at this Q here. Both have an implicit or 0. So this is Q or 0. The other one is not Q or 0. But the Q and the not Q canceled out. So we ended up with 0 or 0. What is or false? It's just false. Okay? So now that we have a false as the conclusion of that, the entire thing is false because it is one big conjunction. What happens when you have false in a conjunction? The whole thing is false, right? So now the biggest mystery of today is, why do we want to prove something is false? I thought we were trying to prove something is true.
Proof by contradiction.
Because we are trying to use proof by contradiction. So that is the linking piece. So I want you guys to read this entire thing over the weekend. Now that we know the big picture, you can read in the other detailed pieces to help connect the big pieces. Yes?
Are we supposed to know how to do a derivation?
I think Boolean algebra is important in this class.
Is there like a resource to understand it better online? Can you think something on the?
I'll see if I can find something.
It was P or 0, right? That part, you said that was P or 0 and Q or 0?
Yep.
Okay.
They're basically the same thing, so a lot of times people just don't write the or 0 because it's just...
Is that what the bar under means?
No, the bar is indicating how I join the terms. What is connecting the terms to...
Oh.
What am I using to resolve?
Gotcha.
Yep.
What's my test there? Do you have any other tests?